The following survive. This is survive. An EJB server crash. Option A, stateful session bean instance. Option B, stateless session bean instance. Option C, message driven instance. Option D, entity beans primary queue. Here correct option is option D, entity beans primary key, and this will survive an EJB server crash. This is common data questions, and the data given for two questions is box P has 6 red balls and 12 blue balls, and box Q has 7 blue balls and 5 red balls. A ball is selected by first selecting a box and then choosing a ball from the selected box. The probability of selecting box P is 3 by 4, whereas box Q is 1 by 4. First question is, what is the probability of selecting red ball? So it is given that box P contains red balls 6 and blue balls 12. The probability of selecting box P is 3 by 4, and the box Q contains 5 red balls and 7 blue balls, and probability of selecting box Q is 1 by 4. Here the first question is, what is the probability of selecting a red ball? So here selecting a red ball can be done from either box P or box Q. So if it is from box P, then we have to select the box P first, and probability of selecting box P is given by 3 by 4, and in that box P there are 6 red balls. So 6 divided by total number of balls is 12 plus 6, 18. So this is from box P, and the red ball can be selected even from box Q also. So box Q is the probability of selecting box Q is given as 1 by 4 into, and the number of red balls in box box Q is 5. So 5 divided by total number of balls in box Q is 5 plus 7, 12. So this is the required probability, and if we simplify this, we will be getting 17 by 48, which is option C. So the second question for the same data is, if a randomly chosen ball is blue, then what is the probability that it comes from box P? Option A is 23 by 48. This is 48. Option A 23 by 48. Option B 1 by 2. Option C 1 by 4, and option D 24 by 31. So the question is, if a randomly chosen ball is blue, then what is the probability that it comes from box P? Here the denominator contains probability of selecting blue balls from total number of cases will include probability of choosing blue ball from box P and probability of choosing blue ball from box Q. So denominator will be probability of choosing box P is 3 by 4, and choosing blue ball in that is, here total number of blue balls is 12 by total number of balls in box P is 18, plus probability of choosing box Q is 1 by 4 into number of blue balls in box Q is 7 divided by total number of balls is 12. 7 plus 5. So this will be the total number of cases. Here the question is, ball should be chosen from box P. Probability that it comes from box P. So numerator will contain probability of choosing a blue ball from box P. So probability of choosing box P is 3 by 4 into, in that box P number of blue balls is 12. So 12 divided by total number of balls is 18. So this is a probability of probability of choosing, if we choose a ball, if we choose any blue ball, probability that it comes from box P. So if we simplify this, we will be getting answer as 24 by 31, which is option D.
Which of the following statements are true? First statement is given as, if G is a maximal planar graph with P greater than or equal to 3 vertices and Q edges, then Q is equal to 3P minus 6. And the second statement, if G is a maximum planar bipartite graph with P greater than or equal to 3 vertices and Q edges, then Q is equal to 2P minus 4. Here in this question, two statements are given and we have to identify which of them is false. The first statement is, if G is a maximum planar graph with P greater than or equal to 0, P greater than or equal to 3 vertices. Here P is number of vertices and Q is number of edges in a maximum planar graph. So let us take one example. Let us take a complete graph with 5 vertices K5, which is non-planar, and if we remove any edge from it, it will be planar. And if we apply this result, that is Q, number of edges is equal to 3P minus 6, this statement will be true. And for the second statement, if we take K3 comma 3 and remove one edge, even that will be true. Or else you can take any planar graph for the first statement, like K4, and if you take example for statement 2 as K2 comma 3, then those two statements will be verified. So here correct option is both 1 and 2 are true, which is option C.
Data, there are two questions on this data. The virtual memory system consists of the address space of 2 × 28 bytes, the memory space of 32 megabytes. The page size is 4 kilobytes. How many page tables can be stored in a given memory space when each page table entry contains 3 additional bits for bookkeeping? So if you want to find out the number of page tables to be stored in a capacity of memory, we need to find out the each page table size. So the logical address space is containing 28 bits. This 28 bits must be divided into two parts. One is the page number, other is the displacement. Displacement is D. Okay, so the page number depends upon the number of pages. So this page number is around page size is 4 kilobytes. 4 kilobytes means 2 power 12. So out of 28, this is 28 bits. So we are having 12 bits for the displacement. 28 minus 12 will be again 16 bits for the page number. Using 16 bits, we can have 2 power 16 pages. When you have 2 power 16 pages, each page page table entry, for every page we have an entry into the page table. So the number of entries in the page table is 2 power 16. What is the size of each entry? Normally 3 bits for bookkeeping plus frame number we have to store. Frame number, what is the physical frame size? That is 32 megabyte. 32 megabyte means 2 power 25. Okay, 2 power 25. This 25 bits must be divided into, again displacement is 12 bits because page displacement is equal to frame displacement. Again 25 minus 12 will be 13 bits for the frame number. Okay, so 13 bits plus 3 bits for bookkeeping, 16 bits. 16 bit means 2 bytes. So every entry is 2 bytes, 2 power 16 entries. That means it is 2 power 17. 2 power 17 bytes is the page table size. Okay, but number of page tables you have to divide it in the memory. So 32 megabyte means, so 2 power 25 divided by 2 power 17. So the number of page table will be 2 power 8. It will be 256. A is right answer. There is another question on the same data. If the memory size is 1 gigabytes, then what is the size of the page table? Option A 168 kilobytes, B 32 kilobytes, C 102 kilobytes, D 192 kilobytes. So we need to find out the size of the page table when the memory size is 1 gigabyte. 1 gigabyte means 2 power 30. So this 30 bits must be divided into two parts. One is the frame number, other is the displacement. Okay, displacement anyway 4 kilobytes is the page size, no, it will be 12. So 30 minus 12, this will be 30, no, 30 minus 12 will be around 18. So for frame number 18 bits we have to use. So each page table entry, there is no change in the logical address space. So how many entries will be there in the logical address? Already we know that there are 2 power 16 entries, because 2 power 16 pages will be there. So 2 power 16 entries into each entry contains how many? Frame number 18 bits plus bookkeeping, total 21 bits. 21 bits. Actually we can write 2 power 16 this as 2 power 16 into this 21 bits can be written as 16 bits plus 5. 16 bit means 2 bytes. Okay, or else in the kilobytes also you can write, it will be directly, if you find 2 power 16 into 21, it will be bits. If you want to find out in bytes, you have to do like this: 2 power 16 into 21 divided by 8 bytes. 8 means it will be around 2 power 16 into 2 power minus 3 into 21 bytes. So this will be 2 power 13, 21 into 2 power 13. So in the form of kilobytes you can write like this: 21 into 2 power 3 into 2 power 10. So 8 into 21. 168 kilobytes you will get. 168. Option A is the right option.
The counter is shown in the figure. We have to decide what is the modulus of this. Here, the output is going to be, see, suppose if we assume an initial state as 0, 0 for this. Whenever the output of the NAND gate is going to be 0, the flip-flop is going to come back to again 0, 0, 0, 0 status. So for that, this has to be 1. So this. So the output is going to be cleared whenever it is going to have a, that is suppose Q3, Q2, Q1, Q0. For this particular combination, it is going to be resetted. So from the 0, 0 to 1, 0, 1, 1, that is, these many number of 0 to 11 means it is a mod 12 quantum. Find the frequency of the flip-flop at Q3 output. That is, f of Q3 is equals to 1.2 divided by 12, which is equals to 1 by 10 megahertz, which is 100 kilohertz. That is, option C is correct.